If it is visible, then I will start it. Okay, so today's topic is steam jet ejector refrigeration system. Now let us first of all talk about its principle. When external pressure on a liquid changes, its boiling point also changes. You must be knowing that if we talk about water, you know at atmospheric pressure it boils at 100 degrees Celsius. If we reduce the pressure, in that particular case, the boiling point will also change. Okay, so it means if I reduce the pressure to say 0.9 bar, then the boiling point may be somewhere around say 92 or 93 degree instead of 100 degrees Celsius. So that is the meaning of the first line actually. Normally atmospheric pressure acts on the surface of the liquid. This you know, if you have a water in a say container, so naturally the atmospheric pressure is acting on its surface. However, if by some means this pressure is reduced, then the liquid will start boiling at a lower temperature. So this is what I wanted to tell you. Suppose if I reduce the pressure to a lower level below that of the atmospheric pressure, then the water will boil at a lower temperature. It could be so low that if I reduce the pressure to such a level, then it can also boil at say 10 degrees Celsius or 12 degrees Celsius. It depends upon the level of the pressure actually. And you also know if we increase the pressure, then the boiling temperature of the water increasing. This is already known to you. So this basic principle of boiling of liquid at low temperature by reducing the pressure on its surface is used in a steam jet ejector refrigeration system. Okay, here it is written as steam jet refrigeration system. So actually it is steam jet ejector refrigeration system. The pure water boils at 100 degrees Celsius at standard pressure of 1.013 bar. It boils at 12 degrees Celsius and 7 degrees Celsius if the pressures are kept 0.14 and 0.01 bar respectively. So it's very clear, if it is 100 degrees Celsius, the pressure is 1.013 bar. And if we want to maintain, we want that the water should boil at 12 degrees Celsius, then the pressure should be 0.014 bar. And if we want that the water should boil at 7 degrees Celsius, then the pressure should be 0.01 bar, respectively. The low pressure or high vacuum on the surface of water can be maintained by throttling the steam through jets or nozzles. Okay, this line will be clear to you when you will see the schematic diagram of the system. So right now, just I will not explain it. Okay. Now let us proceed further. Water, like air, is a perfectly safe refrigerant. You know, it doesn't cause any ozone depletion, neither it causes global warming. So it's a safe refrigerant. At low temperatures, the saturation pressure of water is low and specific volume is high. So naturally, when the pressure will be low, the specific volume increases. This, you know, when we studied about vapor compression cycle, I told you about the importance of the atmospheric pressure. If the pressure is lower at the entry to the compressor, in that particular case, the specific volume is high. So same thing happens here also in case of steam jet ejector refrigeration system. If the temperature, if the pressure of the water is low, correspondingly the specific volume will be high. The temperature which can be attained using water as a refrigerant is not low enough for most of the applications. Okay, you know that the freezing point of the water is 0 degrees Celsius. So for most of the applications, if we want to use water as a refrigerant, in that particular case, we cannot go for very low temperatures. Okay, we have to operate the system above 0 degrees Celsius in any case. With water as a refrigerant, it can be used for air conditioning. So naturally, you cannot go for refrigeration purpose, because in case of refrigeration, you will have to operate the system below the 0 degree Celsius, whereas in case of air conditioning, even if the water is available at around 5 degrees Celsius, 7 degrees Celsius, it can be used for conditioning the air or reducing its temperature. The large volumes can be dealt with by means of a steam jet. Once again, I will talk about it later on. The steam jet can be applied to high temperature cooling and can be adjusted quickly to meet variations in load. So basically the meaning is if we are using a jet of steam, then we can also vary its quantity to meet the variation in the load. Load means cooling load actually. So cooling load can be taken care of by varying the quantity of the steam which is entering into the system actually. Steam jets are used when required temperature is around 5 degrees Celsius. So I have already told you when we will be using steam jet ejector refrigeration system, we usually will be going for a temperature range of 5 to 7 degrees Celsius or 10 degrees Celsius. That is where we usually use this steam jet ejector. The steam jet refrigeration cycle is quite similar to conventional refrigeration cycle with an evaporator. Number one, a compression device. It is not a compressor here, it's a compression device, different from a compressor, a condenser as the basic system components with a refrigerant for producing cooling effect. So nearly all of these components are available in case of a vapor compression system also, but here we are not using a compressor like in case of a vapor absorption system, but there is a ejector which is taking care of the increase in the pressure actually. Okay, the ejector refrigeration system, instead of mechanical compression device, employs a steam ejector or booster to compress the refrigerant to the condenser pressure level. Water is used as the refrigerant and the cooling effect is produced in the steam jet refrigeration continuous cycle by vaporization by a part of the water in the evaporator at a low absolute pressure level. This I will explain you when I will show you the diagram. Now this is the schematic diagram of a steam jet refrigeration system. So first of all, let us see what are the various components so you can acclimatize yourself to what is a steam jet ejector refrigeration system. So first thing that you can see here is evaporator or the flash chamber. So this is you know already. Then you know about the condenser also. This is also present in case of a vapor compression system. Besides this, we have the other components. What are those other components? We have a boiler. Steam is coming from a boiler here. So that means boiler is also a part of steam jet refrigeration system or steam jet ejector refrigeration system. Why I am calling ejector? Because you can see there is a component with the name ejector actually. And basically this ejector is increasing the pressure of the refrigerant from the evaporator pressure to the condenser pressure. Okay. So boiler, evaporator, condenser, ejector, four components. Then you can see there is a nozzle at the entry to the ejector. Besides that, if you will see, there are various components whose names are given here, but they are not shown actually. For example, if you see this particular line which is coming out from the condenser, it is nothing but two condensate pump and two boilers. So basically the steam which is condensed in the condenser is passed through a, you can say, a pump here, and from the pump it goes to, let us say, if we have a boiler here, and from the boiler the steam goes to the ejector. Okay, so these are the components, and there is a circulating pump. Actually, as I told you, the water is being used in this particular system, and this part is the evaporator where the chilled water is present actually. So chilled water is circulated with the help of a circulating pump, and here we have the cooling load actually. This is the cooling load. Let us say this is the cooling load which we have to take care of. So basically the water is taking heat which is equivalent to QE, and it gets warm and once again sent back to the evaporator or the flash chamber. So till now I haven't explained you how it works, but I am just trying to tell you the various components actually. So don't worry, I will explain you. Now, I was also trying to explain you about the principle. So what I would like to tell you is, if you will focus your attention on the evaporator part here, this part here, this is the evaporator. Now what happens in case, normally if you see, the water in any container is under the atmospheric pressure. But what we are doing in this particular case is we are maintaining a very, very low temperature, very, very low pressure actually in this particular evaporator chamber or the flash chamber. Okay. So here the pressure is very, very low. Now what happens actually, the steam which comes from the boiler passes from the nozzle and its velocity is very high at this particular location. Okay, at this particular location, the velocity of the steam is very high. So what will be, it will do? It will actually entrain the water vapor. Now you see here, here you can see there are certain nozzles which are spraying the warm water, okay, which is coming from here. So nozzles are spraying the water. So the water being sprayed is actually evaporated because of the high velocity steam which is coming out from the nozzle. So it basically entrains the moisture and it converts that moisture into steam, and the heat required for converting that moisture into steam is taken from the water which is present here. Okay. So once again, I would like to explain you. So what happens actually when you when this heat is taken from the water actually cools down by a certain degrees. Okay, so I will explain you once again. uh, Let us see.
हेलो सर.
Yes,
हेलो. हाँ
yes,
सर,
tell me.
ये हाँ सर, एक स्टूडेंट ना ज्वाइन करना चाह रहा है सर. एक्चुअली वो ऑफिस से लेट हो गया था, तो उसका मैसेज आ रहा है सर बार बार.
See, actually I have already told that you should join early actually. Just wait. But yeah, okay.
ओके, थैंक यू.
Okay, so okay, so once again I will explain you when I will come to this diagram. Now what are the advantages of the system? This is a simple and rugged in construction system. It's a vibration-free system. It's highly reliable, low production cost, low maintenance, safe, non-poisonous, non-flammable refrigerant, low running cost, less than 50% compared to vapor compression system for higher tonnage greater than 70 tons. Load variations are quickly adjusted and it is suitable for process industries, steel plant, petroleum plant, and thermal plant. So it has many advantages. As you can see, it's simple, there is no vibrations, reliable, low production cost, low maintenance, non-poisonous, safe, non-flammable, low running cost, very important. Load variations means if we are varying the evaporator load, then it can be quickly adjusted and it is suitable in many places like process industries, steel plant, and petroleum plant and thermal plant. Now, what are the disadvantages? Not suitable for water temperature below 4 degrees Celsius. Maintenance of high vacuum in evaporator is necessary. As I told you that at low temperature, we are actually evaporating the water. So that means the pressure is below the atmospheric pressure. Okay. And it is achieved by the direct vaporization of the water to produce chilled water, which is limited as a very large volume of vapor needs to be handled. Okay. Large sized condenser is required since the magnitude of heat transfer is 3 to 4 times than those of vapor compression system. COP lies between 0.4 to 0.6, requires either a centrifugal compressor or ejector device for the compression purpose. So as you know, we are not using the centrifugal compressor, we are using the ejector in this particular case. Since centrifugal compressors are expensive, ejectors are used. That is the reason why we are not using a centrifugal compressor. Centrifugal compressor can be used because it is capable of handling large volume flow rates. And when the volume, if we talk about the water, in case of water, the volume is very, very high in case of when it is converted to steam actually. So we can use centrifugal compressor, but rather than centrifugal compressor, we use the ejectors because ejectors can handle large volume flow rate. But the problem is the efficiency of ejector is low. Therefore, it renders the complete system inefficient. Inefficient means its overall COP will be less actually. Okay. Now there are certain applications which you can see it can be used in food processing for pre-cooling of vegetables and concentrating fruit juices, gas plant, breweries, rubber and vulcanizing industries, paper and pulp industries. So you need not to worry, but you should know about the application part also. Okay, now let us talk about working of steam jet ejector efficient system. Okay, once again, before I explain this, I would like to see this particular system. Yes, it is here. I will explain you once again. See, suppose I am maintaining a temperature of say 5 degrees Celsius here in the system. So what will happen? The pressure here is quite low. So it could be, as I have told you earlier, it is 0.01 bar, 0.01 bar. Okay. And the steam here is entering at a pressure of somewhere around, let us say 1.2 bar. Okay. And you can see there is a nozzle here. Here the pressure from the of the steam from the exit from the boiler was, let us say 8 bar. So it is being passed through the nozzle where its pressure is dropping to 1.2 bar. So when the pressure drops, the steam which is coming out of the nozzle, it is at a very high velocity, is at a very high velocity. So the steam which is coming from the boiler is known as motive steam. It is known as motive steam. Okay. And here the chilled water which is being circulated, this chilled water which is at 5 degrees Celsius, it is being circulated with the help of a circulating pump to the cooling load. So basically we have somewhere here the cooling load from which could be at a temperature of, let us say, 10 degrees Celsius or say 20 degrees Celsius. And this chilled water is at 5 degrees Celsius. So heat transfer is taking place from the cooling load to the chilled water which is available here. Okay. So this is how the heat transfer is taking place. So the cooling load means the products which we have want to cool or something else which we want to cool. So after the water takes the heat from the cooling load, its temperature increases, and this hot water is being sprayed with the help of the nozzles here. So these are the nozzles. This is a nozzle. All these are nozzles which are spraying the water. So it's you can say the minute droplets are coming out from the nozzles. And here you can see from the uh, nozzle, the steam at high velocity is coming out. So what it will do? It will try to suck this moisture or the minute droplets of the water, and it will convert them, and these minute water particles will be converted into vapor while they are being sucked here. Okay. And for conversion of these vapors into for the conversion of these water particles into vapor, it will require heat actually. So from where they will take the heat, these are coming down actually, these are coming down, but these are sucked up. Okay. These particles are sucked up, and for conversion into vapor, they will take the heat from the water which is available here. So what will happen? So basically, the water particles are taking latent heat, and this latent heat is coming from the water which is available here. So what will happen? The temperature of the water will reduce to 5 degrees Celsius. Okay, will reduce to 5 degrees Celsius. So automatically the load will be taken care, and once again this water will be reaching to 5 degrees Celsius, and once again it will be circulated here. Now, what exactly happens after this? After this, the vapors which are going towards the steam, because the steam is sucking these vapors, they mix here. Here we have a mixing area. This is the mixing chamber, you can say. So the steam, high velocity steam and the entrained vapors which are coming from here, they mix at this particular section, which is known as the mixing section. And after that, it enters into this ejector portion. Now you can see the shape of the ejector. It is diverging actually. Now you know what happens. The pressure at this particular point is quite low. Okay, you can say, though I have said that the pressure here is 1.2, but we can go to a very low pressure also. Say if the pressure here in the evaporator is 0.01 bar, we can go to 0.02 bar also. So that means it's a very low pressure. Once this mixed vapor which are coming from the water, from the evaporator and the boiler, they mix here, and once they reach the ejector portion at this particular location, after that we have a diverging section. Here in the diverging section, what exactly happens is, because the area is increasing, so whatever is the velocity, that actually reduces. Velocity of the steam which is carrying the entrained vapor also, its velocity reduces, and that reduction in velocity causes the pressure to increase up to the condenser pressure. Okay, the condenser pressure is about, you can say, 55 millimeter of mercury column. 55 millimeter of mercury column. Okay, so this much pressure increases. Once it increases to this particular pressure, what we are doing in the condenser, we are circulating the cooling water here. The cooling water takes the heat from the steam, and the wastewater goes to the cooling tower, where it is cooled once again, and once again it is fed to the condenser. And whatever the condensed steam which is coming out from the condenser with the help of a condensate pump is sent back to the boiler, where the energy is supplied in the boiler, and once again the steam is produced, which once again goes to the nozzle, and this is how the cycle keeps on working. One more thing I would like to tell you here. See, in the evaporator, you can see there is a certain amount of the evaporation taking place. Okay, certain amount of the evaporation takes place. So when evaporation will take place, there is loss of water in the evaporator. That loss of water in the evaporator is taken care by supplying the makeup water here. So here we are supplying the makeup water to the evaporator, because certain amount of the water has evaporated from the evaporator or the flash chamber, and that is lost, or that goes to the boiler, or that goes into the atmosphere from somewhere. Then one more thing you can see here, we have, because you can see this makeup water is entering here. It's the open pipe, you can say. Not open pipe means air can also enter through this. So we have to actually take care of the air also which is entering into the system. So we have air ejectors here. So what air ejectors will do, they will create the vacuum here. Okay, air ejectors are also the ejector which is shown here. See, it could be something like this, air ejector, double air ejectors are there. So we will also try to suck the air from here, and this air along with some part of the steam will be sucked actually, and that will be thrown out of the system actually, because air actually will increase the pressure in the condenser that we don't want actually. For that we are using an air ejector in this particular case. So I hope I have tried to explain steam ejector efficient system here. And once again, in the few more slides, this is explained once again. Okay. So once again, I am coming back to the basic components. Basic components, once again, you can see here, it's a evaporator. You can see the evaporator part is here. It's evaporator or the flash chamber. Steam ejector, also known as the booster. This is steam ejector. Then condenser. This is the condenser we have. Then a two-stage ejector, non-condensable pump. So this is the air ejector or the two-stage ejector, which is used for removing the non-condensable gases from the condenser, and that is basically air which cannot be condensed in the condenser. Then we have the chilled water circulating pump, and this is the chilled water circulating pump here. Then condenser condensate pump. So whatever is the steam which is condensing, with the help of this condensate pump is sent back to the boiler, and the remaining things are the necessary valves and the control. So I hope these components are clear to you. Now let us move to the working of the system. The motive steam from the boiler. So the steam which is coming from the boiler is actually known as the motive steam, expands through the nozzle of an ejector, and this is at a pressure of 1.7 to 8 bar. So steam is about at a pressure of 1.7 or 8 bar, means it can vary between these pressure ranges, and the pressure at this particular point will be somewhere around 0.015 or 0.012 bar. Exactly, means approximately this could be the pressure. And as I told you, the pressure here is uh, yeah, rather I would say the pressure here will be even lower than the pressure which is here existing in the chilled water tank, actually chilled water or the evaporator. If I say the pressure here is 0.01 bar, so the pressure here is even lower than this, say 0.009. Okay, because if the pressure here is lower, then the vapor has automatically the tendency to move to a lower pressure area, actually. Okay, so even if there I was a little bit wrong, actually. Okay, so what happens actually? The high velocity vapor imparts momentum to the vapor of the flash chamber. Thereby, the flash vapor moves along with the motive steam through the ejector. So it is the motive steam, and here we have the flash vapor, which is being sucked by the steam which is coming out from the nozzle. The process of momentum exchange between the flash chamber vapor and the motive steam, and carry over the former by the later, is known as the process of entrainment. So basically, the flash vapor is entrained here by the steam which is coming out from the nozzle. Entrainment is a irreversible process due to which the kinetic energy of the motive steam is considerably reduced. So the kinetic energy of the steam will be reduced because of this irreversible process of entrainment. Additional reduction in kinetic energy occurs due to mixing with the flash vapor. So how the kinetic energy will be reduced? It will be reduced because the mixing of the flash vapor and the steam takes place here in the mixing section. It is not shown here. It will be shown in the next slides later on. Okay, I hope this is clear. The vapor mixture is finally compressed in the ejector to the condenser pressure, where the circulating water causes its condensation. So as I told you, once the mixing takes place between the steam and the flash vapor at the mixing section, this is the mixing section just before the throat of the ejector. After that, the mixture passes through the this diverging portion of the ejector, where because of the increase in the area, the kinetic energy reduces and the pressure increases to that of the pressure which is existing in the condenser. And what happens in the condenser? We are circulating the cooling water here, and the cooling water takes the heat from the steam, and here we are left with the condensate. Okay, the condensate is then pumped back to the boiler pressure with the help of the condensate pump. Now let us talk about the chilled water. What happens to the chilled water? Once again, because there is entrainment of the flash vapor from the surface of the from the moisture which is being coming out from the nozzle, which is being sprayed by the nozzles, it is being sucked by the high velocity steam, and the energy required for the conversion of this wet vapor wet vapor, or say moisture, if you call it, this moisture requires certain amount of the heat, and that heat it takes from the water which is available here. So when it takes the heat, latent heat from the water which is available here in the evaporator, the temperature of the chilled water drops to 5 degrees Celsius, and once it drops to 5 degrees Celsius, it is circulated here with the help of the circulating pump, goes to the cooling load, and once it goes to the cooling load, it takes the heat QE, okay, and once again it becomes the warm water, and once again it is circulated, it is being sprayed through the nozzles here, okay. Since cooling is due to vaporization of water, the makeup water is supplied for keeping a constant water level in the flash chamber. This is the makeup water which we are supplying in the flash chamber. In steam jet refrigeration system, the control of capacity is possible either by throttling the steam inlet pressure or by providing more than one nozzle operating in parallel, each driving a certain amount of the vapor from the flash chamber. So the meaning is, suppose the load varies at this particular point. Suppose initially it was say 1 TR. Now suppose it increases to say 2 TR. So when it increases to 2 TR, we need to evaporate more amount of the flash vapor here. And to increase the amount of the flash vapor, which is going to the ejector section, what we need to do is we need to, suppose initially it was operating at a pressure of 2 bar. So the velocity here is corresponding to that particular value. Suppose I say the velocity at the nozzle is V2 and its value is 50. I'm just taking some approximate values. I don't know what the exact values. Okay. So 50, if I am saying, is the velocity here. So it is, suppose it is entraining vapor corresponding to 1 TR. Now the load is increased to 2 TR. So what I will do, I will increase the pressure here in the boiler to, let us say, 3 bar. So what will happen? This velocity V2 will now increase to say 100 meter per second. So when its velocity is increased to 100 meter per second, it will entrain more amount of the vapor from here. When it will entrain more amount of the vapor, that means now it is capable of cooling the water to even a lower value. So this will be able to, this lower temperature of the water will be able to take care of this increased load actually. Or if you want that there is some other system, you can go for more number of the nozzles here. It's a single nozzle, you can go for more number of the nozzles here. There may be 2 nozzles, 3 nozzles, 4 nozzles in parallel actually. And once more amount of the steam is passing through the nozzles, then more amount of the vapor will be entrained from the flash chamber, and that is how we can take care of the cooling load actually. This is how we can change the cooling load, take care of the cooling load. I hope this much is clear to you. If you have any doubt till now, you can ask.
Sir, the throttling process for the water is taking place in the nozzles in the evaporator only.
Correct. You want to say, if you see this diagram, basically the pressure is being reduced because of the sucking of the vapor actually, because of the sucking of the moisture actually, which is being sprayed by the nozzles. And because of this suction effect, there will be low pressure in the evaporator or the flash chamber. Okay.
And sir, not by the sprinklers over the chilled water. They are also reducing
See,
pressure.
no. Sprinklers are not reducing the pressure. It is because we are sucking the. See, there are two things actually. See, first of all, the pressure here is already, let us say, 0.009 bar. Okay, and the pressure here which we want to maintain, because we want to maintain low temperature here. See, initially when we will start the system, it will be at high pressure, no doubt. Okay, this water is at high pressure, but the moment it starts sucking the vapor, the pressure will keep on reducing here, and after a certain period of state, a certain period of time, when the steady state comes, then the pressure here will be dropped to, let us say, 0.01 bar, and it is higher than the steam pressure which is available here. So automatically the suction pressure differential will be created. Okay, and it's basically, you can say, whatever is the decrease in pressure is taking place, that is because of the motive steam which is coming from the boiler actually. Okay, no other you can say expansion devices here. Okay, you can always reduce the pressure. Suppose if the air is passed with a very high velocity over say some pan which is containing the moisture, so what will happen? The moisture will also be entrained along with the air, and this is because it has the momentum. The air has the momentum. It will create a sort of suction effect, and that suction effect will reduce the pressure over the surface of the water actually, and the water will be evaporated. Okay.
Okay, sir.
Uh,
What you said that the load was at 20 degrees Celsius hypothetically, and the chilled water is at 5. Then the water which is sprinkled over the chilled water is of approximately 10 degrees centigrade. Okay.
okay.
And what
See,
you are
it is
saying that
the reason is when it is being sprayed, yes, it will be at high temperature. No doubt it will be at high temperature. But because of the suction effect, what will happen? This will be evaporated also.
yes, sir, I am
Okay,
asking that only that the nozzle above in the ejector before the ejector, because of this pressure difference, only the whole chilled water gets low temperature.
correct. See, what will
Okay.
happen? Suppose the temperature it is being the water is being sprayed here at 10 degrees Celsius. Okay. So what will happen? क्या होगा यहाँ से? अब इसको evaporation के लिए heat चाहिए. Heat जो है यहाँ से लेगा. अब एक्चुअली मैं एक छोटा सा एग्जांपल देता हूँ. एग्जांपल क्या है? आपको अगर पता हो तो लेटेंट हीट ऑफ वेपोराइजेशन जो होता है 540 किलो जूल और किलो कैलोरीज. आई डोंट रिमेम्बर एक्चुअली. या आई थिंक इट इज किलो जूल.
Yes, sir.
So if I am kilojoules per kg, I think.
Yes.
Okay. If I am evaporating 1 kg of the moisture here, okay. If I am evaporating 1 kg of the moisture here, so I can reduce the temperature of 540 kg of water by 1 degree Celsius. Okay. Because it requires 540 kilojoules. So it will reduce the water temperature by 1 degree Celsius. But if I am evaporating more, or if the quantity of the water here is less, then the temperature of the water can be reduced more actually. Okay.
Okay, sir. Okay.
Okay. So this is how it is working. Now let us see the analysis of the steam jet ejector refrigeration system. Okay. So now I have shown the various state points here also. The steam from the boiler is at state point 1. It is coming out at state point 2 dash. So let us see how the process is taking place. This is the motive steam. So we are considering that this is the saturated steam at the boiler pressure. It is state point 1. And once it passes through the nozzle, you know what happens in the nozzle? In the nozzle, the pressure drops and it gets converted to the kinetic energy. Okay, so basically when the pressure will drop, the process here you can see this is actually TS diagram. It is a TS diagram. So if it is an isentropic expansion, the expansion in the nozzle will take place from 1 to 2. So 1 to 2 shows the isentropic expansion of the steam in the nozzle, but actually it is never isentropic. It is a irreversible expansion. So rather than reaching at point number 2, the steam will be produced at steam at high velocity will be produced at state point 2 dash. Okay. Now the pressure here is low. Now you can see this is the flash chamber pressure. Okay, as I told you. So that means the steam is also coming out at flash chamber. Rather, I would say that in actual sense, practical system, the steam which is coming out from the nozzle will be at a little bit lower pressure than the evaporator pressure, so that it is easy for steam to entrain the moisture from the nozzles actually. Okay. So for the time being, we can consider that the moisture which is being sprayed is at state point 3. You can see here it is at state point 3. It is being at nearly, you can say, at the same temperature actually. Okay. Now what happens actually, once the steam comes out of the nozzle, there is some loss of its energy. Okay, there is some loss of energy due to this because the steam which is coming out from the nozzle is at high velocity. Okay, when it flows a little bit further, there is some loss of energy and it reaches to point number 4, and this loss of energy is because of some sort of entrainment of the vapor or the moisture from the evaporator or the flash chamber actually. This is taking place because of that. Okay. So the steam is now at point number 4. So at point number 4 is just before the mixing section, and the steam and the water vapor which has taken the heat from the chilled water also is at this particular point. So here in the mixing section, the steam and the vapor they mix here and they reach at point number 5. Point number 5 is very near to the throat actually. This is the throat of the ejector. So the steam further moves. Here you can see what is happening. The point number 5 you can see is a mixture point. It is the mixture of point number 3 and point number 4. That is why it is lying between point number 3 and 4. So this is point number 5 here. Now actually in the ejector section at this particular location we have a diffuser section. In the diffuser the area is increasing, velocity is reducing. So area increases, velocity goes down, pressure increases, and this pressure increases to a level of PC, which is being maintained in the condenser. And I have already told you the pressure here is somewhere around 55 of mercury column, but it is not necessarily always be 55 millimeter of mercury column. I'm just giving you an example actually. Okay, it will also depend upon the cooling water which you are circulating here. Okay, so it will depend upon that temperature also. So whatever is the compression which is taking place here in the ejector section, that can either be isentropic. So it can happen from 5 to 6 here. Okay, you see this TS diagram, it can happen from 5 to 6, but in actual practice it can never be isentropic, it would be irreversible. So the process followed will be from 5 to 6 dash. Okay, so it is irreversible expansion. So you can see it is the condenser pressure here, and outside the dome on the right hand side this is the constant pressure line. So rather than reaching at point number 6, the mixture reaches at this particular point at 6 dash, and then it is condensed in the condenser to point number 7 dash. So what is happening here, it is passed after here point number 6, the it follows this particular direction. Okay, it reaches here at this particular point. So this is the uh, state point of the condensate actually. So it is saturated liquid here, saturated liquid water here, and then it is once again pumped back. So you can say it's just like the Rankine cycle here, it is pumped back to the boiler pressure. It's not shown here, but if you want you can always draw it. Okay, and then uh, let us talk about the makeup water now, because there is some mass of the vapor, okay, mv, which has been entrained by this steam. So there is loss of mass here. So we are adding that much mass of water here into the evaporator. So if mv mass is evaporated, we are adding same amount of the mass into the evaporator chamber actually. So now this makeup water is available, let us say at state point 7. These two temperature, this condenser temperature, see this 7 dash is the condensate temperature. It will always be higher than the surrounding water temperature. You can understand this. If the outside water temperature is say 30 degrees Celsius, then this condensate will be at 32 or 33 degrees Celsius. So that is why the temperature of the water which is entering into the evaporator is a little bit lower. So it will be at 30 degrees Celsius. So the moment it enters here, there is drop in its enthalpy. Okay, its enthalpy is reduced. Sorry, not enthalpy is reduced. Because of the suction which is being created, its pressure is dropped actually. Okay, and it reaches here at state point 8 actually. Okay, so this water is available here at state point 8, and this is also the flash chamber pressure. Okay, and the point number 3, I have already explained you. This is also at the same flash chamber pressure which we are maintaining. And basically this pressure is being maintained because of the steam which is moving out of the nozzle with a very high velocity actually. So I hope all the points are clear to you. If you want to ask anything, you can ask.
So here we are not directly maintaining the temperature of the refrigerated system, the source, but we are maintaining only the temperature of the chilled water only.
Correct. See, chilled water is being used for cooling the load actually. Okay, chilled water is being used for cooling the load.
Yes, sir. But if the load increases, then what will happen if the load increases?
See, if the load will increase, I have already told you we will increase the steam flow
Nozzle.
rate which is
Okay.
coming, yeah, from the nozzle. Okay,
Okay, sir.
that
Okay.
see, whenever we are using such a system, naturally we will have to take care of it by using some sort of arrangement actually. If the load is reducing, then we can actually throttle the steam. When we will throttle the steam before it goes to the nozzle, okay, in that particular case, the pressure at the base of the nozzle will reduce actually. When the pressure at the base of the nozzle will reduce, the velocity of the steam coming out from the nozzle will reduce. In that particular case, the mass flow rate, which is being sucked into the ejector, will reduce, and accordingly, the lower load will be taken care of by throttling the steam actually. Okay.
Okay, sir. Okay.
Once again, now we have shown this diagram. This will come once again later on. So let us see further. So you can see this diagram here. Corresponding diagram is shown here. Both TS and PHS diagrams. The point 1 represents the initial condition of the motive steam before passing through the nozzle, and point 2 is the final condition of the steam, assuming isentropic expansion. So this is on the HS diagram. You can see this is the saturated steam, and it is expanded up to point number 2, but actually it is this is 2 dash, so it goes up to 2 dash because it is not reversible adiabatic expansion. And then I have told you, because of the entrainment process, there is some loss of the energy of the steam, so it reaches at point number 4. And the water which is being sprayed to the nozzles is at state point 3. It is state point 3 here on the TS diagram. And these two, 4 and 3, mix in the mixing section, and we get the point number 5. This point number 5, if it is compressed isentropically, then it will reach at state point 6, though it is shown here on not on the saturation curve. It should have been on the saturation curve actually, because it is shown. Okay, here also if you see, this is within the two-phase region only. Okay, so here also that is why it is shown in the two-phase region actually. And this 6 dash, this is 6 dash, this is actually irreversible compression in the ejector. So we are getting the point number 6 dash out of the saturation curve. I hope you understand this HS diagram also. Do you know about it? Have you studied this diagram? Tell me. Do you know? Roll number 42.
So
Yes,
on this HS diagram, if we want to show like the point number 7 and 8 is not shown in the
correct.
diagram.
Yes, we can always show that those points here also, but they are not shown here. What I will do, I will draw a diagram showing the point number 7 dash and 7 also. Basically, 7 dash can be shown easily. Actually, if you will see this diagram, I will see somewhere if I can show you. Okay, this is the diagram actually. Actually, if I draw this diagram completely, then it is something like this. It is something like this. Okay, and this is the condenser pressure here. So once this is the entry to the condenser, and it is cooled, so it will go here. It will be coming at this particular point. So this will be 7 dash. Whereas if you see this particular line, okay, this is the evaporator pressure, this is condenser pressure, and this is the boiler pressure. So point number 7 will be, you can say, somewhere here. Okay, either here or at this particular point. So this is the location of the makeup water, state point of the makeup water. So it will go like this. Okay, whereas the steam which is condensed goes like this on the HS diagram. Actually, whatever the Mollier chart which you have used earlier, it doesn't shows the complete HS diagram actually. And the diagram which I have drawn here is, this is the diagram. I will also draw it actually. See if I will draw it here. So this is HS. So we can draw it like this. Okay. And the critical point is here actually. This is the critical point, and these are the lines of constant dryness fraction. Okay, these are the dryness fraction lines, and so on. But actually, in the Mollier chart, the diagram is actually shown from this particular location here. Okay, whatever the Mollier diagram which you have seen, that start from this particular green line and towards the right hand side. The left hand side is not shown. Okay, because that is not required actually. So they are not showing it. But if you will refer to the PK Narg's book and you would like to refer to Rankine cycle, देख लेना, उसमें ये पूरा का पूरा डायग्राम बना रखा है. ओके, तो वहां से देखो, आपको समझ में आ जाएगा. ओके, सो लेट अस प्रोसीड फर्दर.
So PK and heat and mass transfer.
No,
Thermodynamics.
thermodynamics. Yeah, it's chapter number I think 11 or 13. Okay, steam cycle जिसमें है ना, वहां पे देख लेना. Okay, so once again, point 4 represents the condition of the motive steam just before mixing with the water vapor. The point 5 is the condition of the mixture of high velocity steam from the nozzle and the entrained water vapor before compression. I have explained you already. Okay, so once again the same diagram on a bigger in a bigger size. Okay, and point number 6 is the final condition of the mixture discharged to the condenser after assuming isentropic compression. The makeup water is supplied at 7, in which temperature is slightly lower than the condenser temperature, and total to point number 8 in the flash chamber. Okay. Yeah, it may be noted that due to certain unavoidable losses during expansion and compression, the actual expansion of the motive steam is represented by 1 to 2 dash. आपको पहले ही बता दिया, ये 1 से 2 dash में होगा, आइसेंट्रोपिक नहीं है. Actual compression जो होगा, it will be represented by 5 to 6 dash, क्योंकि आइसेंट्रोपिक नहीं है. Okay. Okay, now these are some of the efficiencies which are important in this particular analysis. वो कौन कौन सी efficiency हैं? एक है nozzle efficiency, उसके बाद है entrainment efficiency, और तीसरा है compression efficiency. Okay, so let us talk about these efficiencies. Now nozzle efficiency. What is nozzle efficiency? It's quite easy. You know, if you see here, this is point number 2 dash. So 2 dash enthalpy here is higher than H2. Okay, this is a higher value. So H1 minus H2 is the ideal enthalpy drop, and the actual enthalpy drop is H1 minus H2 dash. Okay, and the nozzle efficiency is defined as actual enthalpy drop divided by isentropic enthalpy drop. So it is H1 minus H2 dash divided by H1 minus H2. And the efficiency of nozzle varies between 80 to 90%. The second efficiency is entrainment efficiency. The water vapors formed in the flash chamber has negligible velocity compared with the velocity of the steam coming out from the nozzle, which is calculated as given below. So we are talking about, I will show you here. See, we are talking about this particular state point and this particular state point actually. Okay, so here the enthalpy is H1 and the velocity is V1, if it is written V1 or C1, whatever it is written. So V1 और C1 दोनों में से जो भी है, और यहाँ पे जो enthalpy है वो है H2 और velocity V2 या C2 जो भी मैंने आगे यूज किया है. Okay, so let us see. So in the nozzle, yeah, we have used C actually. So which equation we are using for the nozzle? Actually, we are using this particular equation, delta Q minus delta Ws is equal to dH plus bke plus bpe. Okay, so you know, if it is a nozzle, we are considering it to be adiabatic, so there is no heat transfer. nozzle there is no shaft, so no work, and we are left with the enthalpy change, kinetic energy change, and we are considering that the nozzle, the change in potential energy is not there, so we are neglecting it. So we are left with only two terms. So we will get h1 plus c1 square. I think there has to be a 2 also because it's the kinetic energy term, c2 by c2 square by 2. So h2 dash plus c2 square by 2. Okay. So that is why, as I told you, at the entry to the nozzle, this velocity c1 is negligible. So it is neglected here. So if I have to calculate this value c2, okay, this c2, this will be equal to h1 minus h2 dash into 2 under root. So this is what you get. This is how you calculate the velocity of the steam. Okay, so we can calculate the velocity of the steam by using this entrainment efficiency. Yeah, it is not the entrainment efficiency, but rather we have just calculated the velocity of the steam. Entrainment efficiency will come next. Now the quantity h1 minus h2 dash is equivalent to the kinetic energy of the motive steam now available for entrainment of the vapor in the flash chamber actually. Okay, so whatever is the kinetic energy which is produced or the velocity which is produced, that is capable of entraining the vapor from the flash chamber. The process of giving the momentum to the water vapors formed in the flash chamber by high velocity steam is known as entrainment of the vapors. During the entrainment, the steam will lose some energy. So as I told you, it reaches from 2 dash to point number 4. So some loss of energy of the steam is there, and this loss is due to entrainment process. Okay, so that is actually defined as the entrainment efficiency. Now, in actual practice, the energy which is available for entrainment is h1 minus h4. But actually, at the exit of the nozzle, this was the energy h1 minus h2 dash. Okay, this was the energy which was actually available at the exit from the nozzle actually. But after, because the steam moves, the energy which is available for the entrainment is this one only, this much only, h1 minus h4. So that is why we define an efficiency which is known as entrainment efficiency by the term, by the ratio h1 minus h4 divided by h1 minus h2 dash. So you can see even this value h1, this is h1 and this is h4. h4 is higher than h2 dash. So this difference is greater than h1 minus h4. So entrainment efficiency in this particular case of steam injector is somewhere around 65%, maybe taken around this much value. It's not very high actually. Okay. Then once again this diagram. Now we will talk about the compression efficiency. Now after the mixing, we are the mixing at the entry to the, at the exit from the mixing section, the steam is at point number 5. This is wet steam now. Okay, this is wet steam. Now this is compressed to point number 6 in the ejector. So it's not isentropic. So actually the compression efficiency is given by the actual value of the enthalpy increase, which is given by it's I think wrongly written. It should be written as though it will not create any problem, it should be written as h6 dash. Okay, just a minute. Yeah, h6 dash minus h5, and above it should be h6 minus h5. You can see it here. Say 6, the enthalpy is h6. h5, this is low value of the enthalpy. Okay, h6 is higher, or 6 dash, this is 6 dash actually. 6 dash, this is 6. So 6 is lower. So h6 minus h5 is lower value. So this is the lower value and this is the higher value. Okay. So this is written as h6 minus h5. Otherwise, even if we have written this way, this will not create any problem because the negative signs can be taken out and it will cancel out actually. Okay. The compression efficiency is taken as 75 to 80%. The compression efficiency is also known as diffuser efficiency. Okay, let us proceed further. MS is the mass of the motive steam supplied in kgs per minute. So we are supplying MS mass of the steam which is going from the boiler to the nozzle actually. and mv is the mass of the water vapor formed in the evaporator or the flash chamber. So the mass of the water vapor which is generated here due to the entrainment is mv. So what will happen? What will be the total mass at that cross section? Because this is the steam which is coming out, it has ms mass and this mass is entrained here. So the total mass here will be equal to ms plus mv. So m mix is the mass of the mixture of compression in kgs per minute or per second, you can take anything, and it is equal to ms plus mv. Now what is the energy which is available for the compression? See, the steam was entering the boiler at state point 1, and at state point 4 this is the you can say the final energy of the steam before the mixing takes place. So this much is the energy of the motive steam which is available to us for the entrainment process actually, or for the compression process actually. Okay, entrainment and compression, everything for the compression actually. So how much energy is required for the compression? When we are doing the compression, the total mass which is available at this particular point is ms plus mv, and the entry to the ejector is at point number 5 and exit is at h6 dash. So energy required for compression should be equal to m total mass into m6 dash minus m5, and that will be given by ms plus mv into h6 minus h5. That is the energy required for the compression, and this compression will be taken care by this amount of the energy. Now, according to the law of conservation of energy, the available energy for compression must be equal to the energy required for compression. Okay, so this is the energy of the motive steam which is available to us, and this is the energy which is required for compression process. Okay, and now further we have to utilize the nozzle efficiency, entrainment efficiency, and the compression efficiency and modify this equation. And what exactly we want to calculate is the value of mass of the motive steam required per unit mass of the vapor which is generated in the evaporator. This is our requirement. We want to calculate this particular value. And if you see this particular equation, we have both the terms. ms is also available and mv is also available. So we would like to calculate this particular ratio ms by mv, mass of the motive steam divided by the mass of the vapor. Okay, तो हमें ये जानना है कि कितनी मोटिव स्टीम चाहिए होगी अगर हमें यूनिट मास वेपर का जनरेट करना है. तो अब देखो इसमें इक्वेशन नंबर 3 में कुछ टर्म्स हैं, हम उनको चेंज करने की कोशिश करेंगे. अब देखो नोजल एफिशिएंसी क्या था? नोजल एफिशिएंसी की वैल्यू है h1 माइनस h2 डैश डिवाइडेड बाय h1 माइनस h2. सो अगर हम यहाँ से कैलकुलेट करें तो h1 माइनस h2 की वैल्यू कितनी आ जाएगी? इट इज it will go to this side, so h1 minus h2 dash is equal to nozzle efficiency into h1 minus h2. I hope this is clear. अभी आगे देखते हैं क्या हुआ. हमें एक्चुअली में पहुंचना कहाँ पे है? हमें h1 माइनस h4 पे पहुंचना है. हमें इस टर्म पे पहुंचना है. इस टर्म को हमें नोजल एफिशिएंसी, कंप्रेशन एफिशिएंसी और डिफ्यूजर एफिशिएंसी और इजेक्टर एफिशिएंसी की टर्म्स में लिखना है h1 माइनस h4 को. तो देखते हैं आगे कैसे करेंगे. उसके बाद क्या है? इंट्रेनमेंट एफिशिएंसी जो हमने डिफाइन किया था, वो हमने डिफाइन किया था h1 माइनस h4 डिवाइडेड बाय h1 माइनस h2 डैश. डायग्राम पीछे देख लो. ये पॉइंट नंबर 4 है, ये पॉइंट नंबर 2 डैश है. दिस इज 2 डैश एक्चुअली. ओके, ये 2 डैश है. तो एक्चुअली में ये एनर्जी है 1 से 4 के बीच की जो हमें अवेलेबल है, जो कि बेसिकली इंट्रेनमेंट के लिए रिस्पॉन्सिबल है. ओके, तो इंट्रेनमेंट में जो लॉस हुआ था एनर्जी का 2 डैश से 4 पे पहुंच गए थे. तो यही हमने इंट्रेनमेंट, हमने एफिशिएंसी डिफाइन किया था h1 माइनस 4 डिवाइडेड बाय h1 माइनस h2 डैश. तो पिछले अब इक्वेशन में आप देखो तो हमने यहाँ पे h1 माइनस h2 डैश निकाला है. ओके, अब यहाँ पे हम इस इक्वेशन से हम h1 माइनस h4 निकाल लेते हैं. तो h1 माइनस h4 की वैल्यू क्या आ गई? इंट्रेनमेंट एफिशिएंसी. ओके, it is equal to, yeah, it is equal to, not equal to sign, इंट्रेनमेंट एफिशिएंसी इंटू h1 माइनस h2 डैश. देख लो, आई थिंक इट्स क्लियर टू यू. ओके, इसके बाद कंप्रेशन एफिशिएंसी ले लेते हैं. तो कंप्रेशन एफिशिएंसी अगर आप देखोगे यहाँ पे तो क्या है? h6 माइनस h5 ये तो नीचे आएगा, डिनोमिनेटर में आएगा, और ये H6 माइनस H5 न्यूमरेटर में आएगा, ये रहा। तो यहाँ पे उल्टा लिखा हुआ है, फिर से डजेंट मैटर। ओके, तो ये वैल्यू आ गई हमारे पास H5 माइनस H6 डैश की, ठीक है, ये आ गई। तो देखते हैं अभी हमने क्या किया है। अच्छा, ये हमारे पास जो इक्वेशन आई थी, देखो यहाँ पे ये है H6 डैश माइनस H5 डैश। ओके, तो ये तीनों एफिशिएंसीज अभी हम यूज करेंगे। मैं अभी नेक्स्ट स्लाइड पे दिखाऊंगा आपको, सब कुछ लिखा हुआ है। ओके, तो ये सबसे पहले इस टर्म को देख लो, ये वैल्यू है H1 माइनस H2 डैश की नोजल एफिशिएंसी की टर्म्स में। ये मैंने इंट्रेनमेंट एफिशिएंसी का फार्मूला लिखा है, और यहाँ से H1 माइनस H4 की वैल्यू निकाली है इंट्रेनमेंट एफिशिएंसी की टर्म में, और ये कंप्रेशन एफिशिएंसी है। और यहाँ से मैंने H5 माइनस H6 डैश, यहाँ उल्टा भी कर सकते हैं, उसकी वैल्यू निकाली है यहाँ पे, ये आ गई। तो आई थिंक अब ये जो इक्वेशन 3 है ना, इसको थोड़ा सा ध्यान दो यहाँ पे, इक्वेशन 3 और इक्वेशन 4 को देखते हैं हमने क्या किया है। तो इक्वेशन 3 से 4 में देखते हैं क्या हुआ है। हमारे पास यहाँ पे टर्म है H1 माइनस H4 जो 3 बनी थी, ये क्या था, ये मोटिव स्टीम की एनर्जी थी जो अवेलेबल थी कंप्रेस करने के लिए। ये कौन सी है, ये जो कंप्रेशन की एनर्जी है, इतनी चाहिए थी, और मैंने बोला था कि ये दोनों एनर्जीज बराबर होनी चाहिए। तो अब हमने यहाँ पे H1 - H4 है, इसको हमने कन्वर्ट किया इस इक्वेशन से। देखो यहाँ पे H1 माइनस H4 कहाँ पे है, ये रहा, ये रहा हमारे पास H1 माइनस H4। तो इसको ध्यान दो, ये इसकी वैल्यू इक्वल है इंट्रीनमेंट एफिशिएंसी इंटू H1 माइनस H2 डैश। तो हमने यहाँ पे ये पुट कर दिया पूरा, इसकी वैल्यू को H1 माइनस H4 की वैल्यू को मैंने पुट कर दिया एफिशिएंसी ऑफ इंट्रीनमेंट इंटू H1 माइनस H2 डैश, और यहाँ पे आ गया MS प्लस MV, और H6 माइनस H5 डैश, H6 माइनस H5 डैश जो है H6 माइनस H5 डिवाइडेड बाय एफिशिएंसी ऑफ कंप्रेसर है, वो यहाँ पे पुट कर दिया। आई होप दिस इज क्लियर टू यू। इसके बाद क्या स्टेप किया है, ये जो H1 माइनस H2 है, इसको मैंने क्या किया है, इस इक्वेशन को यूज करा है, इस इक्वेशन को। तो यहाँ से H1 माइनस H2 की वैल्यू क्या है, एफिशिएंसी ऑफ द नोजल इंटू H1 माइनस H2। तो ये देखो H1 माइनस H2 जो यहाँ पे था, ये मैंने रख दिया, ये वैल्यू पुट कर दिया है यहाँ पे H1 माइनस H2 डैश। तो ये एफिशिएंसी ऑफ द इंक्रीमेंट पहले भी था यहाँ पे, अभी भी है, और यहाँ से नोजल एफिशिएंसी इंटू H1 माइनस H2। अब ये एक पूरी इक्वेशन आ गई मेरे पास, ये MS पहले भी था, अभी भी है, और ये पूरी इक्वेशन बन गई। सो फाइनली आई एम गेटिंग दिस पर्टिकुलर इक्वेशन। अब इस इक्वेशन को मैंने थोड़ा सा सॉल्व किया, तो नेक्स्ट स्लाइड में मुझे यहाँ पे ये इक्वेशन मिल जाएगी जो कि MS/MV है। तो मुझे पता लग गया कि मोटिव स्टीम का कितना मास है जो पर यूनिट वेपर जनरेट करने के लिए यूज होगा। सो दिस वाज वन ऑफ द थिंग्स व्हिच वाज रिक्वायर्ड, सो एंड इट इज नोन एज mass of the motive steam required per kg of the water vapor produced in the flash chamber। ओके, मुझे पता तो होना ही चाहिए कि मुझे कितनी स्टीम चाहिए यूनिट मास के लिए, ताकि अगर लोड वेरी करे तो मैं अकॉर्डिंगली स्टीम का मास वेरी कर सकूं। तो उसी के लिए ये डेरिवेशन की जरूरत थी। ओके, ये हो गया अब हमारे पास। आई होप दिस इज क्लियर। इफ इट इज नॉट क्लियर यू आस्क मी।
Clear, sir, clear.
Okay, so let us proceed further. As discussed earlier, the makeup water is supplied at 7, whose temperature is slightly lower than the condenser temperature, and is throttled to 0.8 in the flash chamber and leaves the corresponding leaves at point number 3। अब देखो डायग्राम में आपको दिखाता हूँ, अगर यहाँ पे है तो okay, see the water which is available here at point number 8। okay, ये जो 3 भी है, अब एक्चुअली में यहाँ से जो भी यहाँ से भी कुछ वेपर उठेगा 8 से। ओके, तो यहाँ पे क्या है, यहाँ पे ये 7 है, ये क्या है, ये मैंने आपको बताया था, ये सैचुरेटेड कंडीशन है। तो मैं इसको कहूँगा HF7, क्योंकि ये लिक्विड की एंथैल्पी है, लिक्विड वाटर की, मेकअप वाटर की एंथैल्पी है, जो कि सैचुरेटेड वाटर है, X = 0 है। ओके, उसके बाद ये थ्रोटल होके गया, थ्रोटल होके कौन से पॉइंट पे पहुंचा, 8 पे पहुंचा, क्योंकि वाटर है। तो इसका मतलब HF7 जो होगा वो H8 के बराबर है। डायग्राम में मैंने आपको दिखाया भी था, ये देखो, यहाँ पे नहीं है, ये देखो, यहाँ पे 7 और ये 8, 7 पे क्या है, ये तो HF ही है ना यहाँ पे, तो HF7 इज इक्वल टू H8। और एक्चुअली में फाइनली इवेपोरेट होके कौन से पॉइंट पे पहुंच रहा है, पॉइंट नंबर 3 पे पहुंच रहा है, ठीक है ना, पॉइंट नंबर 3 पे पहुंचा, इस पॉइंट पे पहुंचा, 3 पे वेपर फॉर्मेशन हो गई है। तो 3 पॉइंट को देखो अब क्या हो रहा है यहाँ पे, 3 पॉइंट पे अगर आप देखोगे तो ये वाली लोकेशन है, ये है, तो यहाँ पे वेट वेपर बन गया है, ठीक है। इसका मतलब इसने जो है जो वाटर था टैंक में पड़ा हुआ, उससे हीट ले ली, तो हीट लेके इसका जो इसमें लेटेंट हीट ऐड हो गई और ये वेट वेपर बन गया है, एंड देन इट इज मिक्सिंग विद द स्टीम इन दी विच इज कमिंग आउट फ्रॉम द नोजल एक्चुअली। तो बेसिकली ये जो चीज है 8 से 3 के बीच में, ये एक तरह से कूलिंग इफेक्ट प्रोड्यूस हो रहा है, यहाँ पे कूलिंग इफेक्ट है QE, जो कि चिल्ड वाटर हमें प्रोड्यूस हो रहा है, यहाँ पे जो वाटर का टेम्परेचर लो हो रहा है, ये वो है हीट, ठीक है। तो अब आई थिंक आगे आपको समझ में आ जाएगा यहाँ पे। तो इसका मतलब ये हुआ कि सिंस द एंथैल्पी ऑफ द वाटर एट 7 इज इक्वल टू द एंथैल्पी ऑफ द वाटर एट 8.8, therefore for each kg of the water vapor formed, heat absorbed is H3 minus HF7 और H3 minus H8। ये कूलिंग इफेक्ट है मेरा पर केजी ऑफ वेपर जनरेशन के लिए। तो ये कह रहा है कि अगर लोड QTR है, देन द मास ऑफ द वेपर फॉर्म्ड, अगर Q लोड है तो वेपर कितना होगा, ये तो ये TR है, इसको मैंने टोटल किलोवाट में कन्वर्ट किया, उसको 60 से मल्टीप्लाई किया, तो ये टोटल रेफ्रिजरेटिंग इफेक्ट आया किलो जूल पर मिनट में। अगर आप किलो जूल पर सेकंड में लेना चाहते हो तो यहाँ पे 60 मत लगाओ, तो ये हो जाएगा किलो जूल पर सेकंड में 3.5167 से मल्टीप्लाई करके। स्पेसिफिक रेफ्रिजरेटिंग इफेक्ट कितना है, H3 माइनस H7 है। मास ऑफ रेफ्रिजरेंट कैसे कैलकुलेट करेंगे, ये जो टोटल कूलिंग इफेक्ट जो हमने टेक केयर करना है, इसकी वैल्यू को हम मल्टीप्लाई कर देंगे, ये देखो ये MV इंटू H3 माइनस H7, ठीक है। तो अगर मैं इसको मल्टीप्लाई करता हूँ तो ये भी टोटल कूलिंग इफेक्ट है और ये भी टोटल कूलिंग इफेक्ट है। 60 को अगर लेना चाहते हो ले लो तो केजी पर मिनट में आ जाएगा, नहीं लोगे तो केजी पर सेकंड में आ जाएगा। तो इस इक्वेशन को यूज करके मैं जो है मास ऑफ वेपर निकाल लूंगा। अगर मास ऑफ वेपर निकल गया तो मैं उसको यहाँ पुट करूंगा, और बाकी सारी वैल्यूज अगर मेरे पास हैं, मुझे मालूम है कि इंट्रीनमेंट एफिशिएंसी कितनी है, नोजल की एफिशिएंसी कितनी है, कंप्रेशन की एफिशिएंसी कितनी है, बाकी स्टेट पॉइंट्स मुझे जो है प्रेशर और टेम्परेचर कंडीशन से मिल ही जाएंगी, एंथैल्पी सारी, तो मेरे पास सारी वैल्यूज हैं, तो मैं वहां से मोटिव स्टीम निकाल दूंगा मैं। तो दिस इज व्हाट इज रिक्वायर्ड, तो यहाँ से मोटिव स्टीम निकल जाएगी, ठीक है। अब कोफिशिएंट ऑफ परफॉर्मेंस निकालना है, तो रेफ्रिजरेटिंग इफेक्ट मुझे मालूम है, टोटल मुझे कितनी कूलिंग चाहिए जो मैंने Q कंसीडर किया था, और हीट रिक्वायर्ड टू मेक MS। अब एक्चुअली में जो स्टीम जनरेट हो रही है, स्टीम कहाँ से जनरेट हो रही है, मोटिव स्टीम तो जनरेट होगी, उसके लिए हमें हीट देनी पड़ेगी, एक वो है। अभी कुछ चीजें यहाँ पे ऐड नहीं की हुई, क्या ऐड नहीं किया हुआ, एक तो जो हमने जो पंप वर्क है, जो कि बॉयलर में वाटर को लेके जा रहा है, वो पंप वर्क को ऐड होगा, वो यहाँ पे ऐड होना चाहिए। तो वो क्योंकि स्मॉल है इसलिए वो शायद उसको लिया नहीं है, उसको हमने यहाँ पे निगलेक्ट कर दिया, ठीक है। तो बेसिकली जो बॉयलर था, बॉयलर में जो स्टीम पॉइंट नंबर 1 पे पहुंच रही है, और यहाँ पे 7 डैश पे था जब वाटर जो है कंडेंसर से निकल रहा है, तो 7 डैश से 1 पे ले जाने के लिए हमें यहाँ पे बॉयलर में हीट देनी पड़ेगी। ये हीट जो है कितनी होगी, जितना भी हम स्टीम जनरेट कर रहे हैं इंटू H1 माइनस H7 डैश, या अगर मैं मान लूं कि ये वाटर जो भी आ रहा है कंडेंसर से बाहर आ रहा है वो HF के बराबर ही है बेसिकली, तो उतना भी ले सकते हैं कि उसी टेम्परेचर पे अगर पहुंच गया, तो हमने ये ले लिया मास ऑफ स्टीम इंटू H1 माइनस HF7। ज़्यादा डिफरेंस नहीं है दोनों में, इसलिए उसको हम ये कंसिडर कर रहे हैं कि जो टेम्परेचर है बाहर के वाटर का और जो स्टीम कंडेंस होकर निकली है, दोनों का टेम्परेचर सेम है, तो H1 माइनस H7 हो गया यहाँ पे, और जो ऊपर कूलिंग इफेक्ट प्रोड्यूस किया है वो है MV इंटू H3 माइनस H7। तो इन दोनों का रेशियो से हमें जो है कैलकुलेशन ऑफ COP मिल जाएगा। और बेसिकली अब ये देखो तो यहाँ पे MV बाय MS की टर्म आ रही है, जो कि हम ऑलरेडी कैलकुलेट कर चुके हैं, पहले हम जो डेरिवेशन किया था।
सर
hope this is
जो फ्लैश चेम्बर से पंप हो रहा है, जो वो उसका पंप का वर्क है, वो इसमें ऐड होगा या नहीं होगा? नहीं होगा ना सर?
एक्चुअली में क्या है कि क्वांटिटी ऑफ वाटर कम है और उसमें हम कोई ज़्यादा प्रेशर तो उसमें रेज कर नहीं रहे, वो भी नेग्लिजिबल होगा। तो
लेकिन
जैसे
जो रेफ्रिजरेटिंग इफेक्ट फ्लैश चेम्बर में मिल रहा है, तो
हम्म,
बेसिकली वो वाला दूसरा वाला सर्किट है जो पंप ले जा रहा है, वो तो
हम्म,
सेकेंडरी सर्किट हुआ ना, उसका तो वर्क वैसे भी कंसिडर नहीं करना चाहिए।
जो हाँ, जो उसका है
फ्लैश
एक्चुअली में देखो
चेम्बर।
क्या, फ्लैश चैम्बर वाला पंप है ना, सर्कुलेटिंग चिल्ड वाटर सर्कुलेटिंग पंप जो
यस सर, यस सर।
है ना। सी एक्चुअली में बात वही है, हमें जो है ना, हमें वो जो पंप लगाया हुआ है ना, सी सी द पर्पस ऑफ दैट पंप, द पर्पस ऑफ दैट पंप विच इज सर्कुलेटिंग द चिल्ड वाटर इज ओनली फॉर द सर्कुलेशन पर्पस, नथिंग मोर देन दैट। अगर मैं चाहता तो मैं क्या कर सकता था, यहाँ पे चिल्ड वाटर है ना, तो मैं यहाँ अगर लोड यहाँ पे है तो मैं डायरेक्टली भी लोड को यहाँ पे सर्कुलेट करके उससे भी सर्कुलेशन से नॉर्मल थर्मोसाइफन सिस्टम से भी हो सकता था। तो मतलब उसका जो पंप वर्क है ना, वो ज्यादा नहीं है, मतलब कहने का मतलब ये है, क्योंकि प्रेशर राइज बहुत ज्यादा नहीं होगा, इट इज ओनली फॉर सर्कुलेटिंग द वाटर इन द सर्किट ऑफ द इवेपोरेटर, कुछ नहीं है उसका पर्पस। ठीक है, सो आई होप दिस इज क्लियर, दिस इज द लास्ट स्लाइड, and if you have any questions you can ask.
So can you once again explain entrainment?
Entrainment,